Hi everybody, it's Ajanette and I'm here to go over effect sizes with you. So effect sizes is part of our chapter 8 lecture. I'm just going to go ahead and pull that up. It's at the very end, and so I want to kind of talk to you about how effect sizes fit in. So we know that, I'm going to go back up a little bit. We know that when we are talking about, hypothesis testing, that what we're really trying to figure out is, do our statistics fall in the critical region? If they fall in the critical region, that tells us that our alternate hypothesis is most likely correct and our null hypothesis is most likely wrong. So the null hypothesis is assuming that there are no differences. So that would be represented by a mean or a value, in this case z-score, that falls here in between those boundaries. If our null is false and there are in fact significant differences and we need to reject the null, then our mean is going to be over here in one of the critical regions. Now, mind you, this is a two-tailed test, so that critical region is divided by both tails. So all a hypothesis test does is it tells us whether there are significant differences. It tells us whether or not our independent variable did have an effect. It tells us whether or not our mean or z-score in this case was in the critical region. But it doesn't tell us how big the effect was. It doesn't tell us the magnitude of the effect. And so that's what we use effect sizes for. Effect sizes actually tell us how big the effect is. So hypothesis testing says, is there an effect? And there either is or there isn't. So there were significant differences or there weren't. We don't say there were really, really, really big significant differences. We just say there were significant differences or there weren't significant differences. The effect size tells us how big the effect of the independent variable was. So when we're talking about effect size, this is helping to address a limitation of hypothesis testing, where the hypothesis testing is focused on, really it's looking at that null hypothesis. So it's looking at the data. Is the data in the critical region or not? But again, it's not necessarily telling us the effect. And so what we want to now explore is, how big is that treatment effect? Is that independent variable having a substantial effect? And that isn't revealed through significance testing or hypothesis testing. It's revealed through effect sizes. So effect sizes overall effect sizes are means by which we look at the magnitude of the treatment effect. So think of it like an earthquake, okay? Where a hypothesis test or a significance test just tells us there was an earthquake. Okay, that's it. It just says yes or no. Was there an earthquake? Wasn't there an earthquake? The effect size tells us the magnitude or the size of that earthquake. How powerful was it? So it's like, giving us, it was a 4.0 or was it 7.6 or something like that, okay? And we're gonna study the first effect size that we're going to study is Cohen's d. Cohen's d is really simple and direct, and it essentially tells us how many standard deviations our effect was, or how many standard deviations did the treatment change the outcome, okay? And so it's a really simple measure because conceptually we understand standard deviations. So our general formula is looking at the mean difference divided by the standard deviation. And again, we're looking at the standard deviation of the population, okay? And then when we apply that to the z-score formula, we're using the z-score formula when we're comparing, you know, you have it two different ways, but we're primarily looking at with the standard error in the denominator, looking to see what is the mean of our particular sample, and then how does that compare to the population mean and the standard deviation of that corresponding population. So again, when we use a z-score, we know the mean and standard deviation of the corresponding population. Now, I want you to note that the smaller the standard deviation, the bigger this outcome is going to be, right? Because when you make your denominator smaller, it gets to go into the numerator more times, so the bigger your effect size is going to be. When you have a larger standard deviation, you're going to have a smaller effect size. That said, okay, so I'm going to give you this as a really good frame of reference. You know how you've heard the saying, size doesn't matter, right? When it comes to Cohen's d, size matters. When it comes to effect size in general, size matters. The bigger, the better. A larger d means a bigger magnitude or a bigger effect size, okay? And, you know, I know some of you might think I'm crass for making that analogy, but it's an analogy that we can remember, okay? Okay, so let's talk a little bit about kind of conceptually what's happening with effect size. So here's your normal, look at the black line, the normal distribution, and there's our mean at 500 and our standard deviation at 100. When we have an effect size, a D of just 0.15, what that's saying is it's shifting our scores. Because it's positive, we know it's shifting our scores to the right, okay? But only by 0.15%. That's not huge, right? So we have a new mean of 515. So 15 divided, or 15, it ends up being 0.15 because that's the full 100 for the standard deviation. So it's only moving us less than 1/4 of a standard deviation. Whereas in this one, when I'm looking at an effect size of a D equals 1, it is transitioning my scores by a whole standard deviation. So this one up here, the D is telling me that my effect is just increasing scores by 0.15 standard deviations. So with a standard deviation of 100, that's just 15 points. This one is telling me it's shifting my scores by a whole standard deviation, okay? And that's significant. So, and I mean significant not in terms of statistical significance, that's powerful, okay? So the bigger the D, in this case 1, the better. The smaller the D, it doesn't move your treatment effect that much, but that doesn't mean it still doesn't meet the threshold of statistical significance. In fact, we don't calculate effect sizes if they're not in the if they're not in the critical region. So we go through hypothesis testing. In the event that we do reject the null and we have evidence to support statistically significant differences, then we would take a follow-up step and do effect sizes. Right now, our only effect size option is Cohen's d. Cohen's d tells us the number of standard deviations that our treatment effect is changing our outcome. And the bigger the D, the better. So the larger the D, the more it's telling us that our, the greater the magnitude of our treatment effect, okay? So here's your Cohen's d formula. I also want to give you reference to here at the very bottom right. It actually is showing you kind of a table. So we talk about small d's, medium d's, and big d's, okay? So small, medium, or large effect sizes, okay, effects. When it's 0.2 or below, then that's considered a really small d, okay? When it's 0.5, anywhere from 0.5 to 0.7, that is considered a medium D. So let me go back. 0.2 to anything below 0.5 is considered small. Anything from 0.5 to 0.79 is going to be a medium D. And then a large D is anything 0.8 and above. Now, I'm going to tell you why my example relating this to our whole kind of scenario of size doesn't matter. The average penis size is 5 to 7 inches. So if you look at these charts, medium as an average, right, 5 to 7, and above that is considered, you know, a large penis to the right in the critical region, and then below that is, you know, a below average size. So I know that a lot of people aren't comfortable using these types of references, but for me, if you come up with another trick in your mind that helps you remember this, great, right? But if you're using this model coupled with what we know about human sexuality, then it can be valuable. And I'm not saying that size matters in the context of human sexuality, because we know that our sexuality is fundamentally reliant upon so many other things beyond size, right? Communication, intimacy, a sense of vulnerability, trust, communication, all of those things factor into how gratifying your sexual relationship is. But if we're just looking at it as a nice memory tool to understand Cohen's D and in general effect sizes, remembering Cohen's D represents an effect size, and with all effect sizes, especially D's, size matters, right? And so hopefully that is kind of a general overview for you, and you can get a feel for Cohen's D and effect sizes. I do want to kind of talk to you a little bit about power too before I part ways with you. So when we talk about power, power is often done before we do a study. And what it is, it's an assessment that kind of tells us how large our sample needs to be, kind of what criteria or assumptions do we need to meet before we're going to be able to detect significant differences. So power is the probability of being able to find those significant differences, or the probability of being able to reject the null, right? And it really is telling us, like, what's your likelihood of finding a significant result, okay? And at the same time, type 2 error is not detecting a significant difference when in fact there is one, or not detecting a treatment effect when there in fact is one. And so power can also be explained as the probability of making a type 2 error too, right? Or excuse me, of avoiding a type 2 error as well, right? So our whole goal as researchers is to find significance. It's to reject the null. It's to say, no, there are in fact differences. And so power tells us kind of what's the probability of being able to find that. And so just like any probability, it ranges from 0 to 1 or 0 to 100%. And we typically want to design a study that gives us at least an 80% probability of finding differences, right? And so what we always want to remember is that with any test, right, we can either reject the null or we can retain the null. So either reject the null or fail to reject the null. And you can divide up those possibilities. Together, it's 100% of all possibilities, right? That either you have significant differences or you don't. So when we talk about power, when we talk about rejecting the null, we're finding treatment effects, and then not finding a treatment effects is failing to reject the null. So when we talk about the null hypothesis being true, right? If we reject the null when in fact it was true, we committed type 1 error. That is by definition type 1 error. Rejecting the null and saying there are differences when they were really not. So it was incorrect, and we call that our alpha level. What's the probability of being wrong? What's the probability of committing a type 1 error? What's the probability that our results are just due to chance and not because of our true treatment? And we want to hold that as best as we can. No more than a 5% probability, but as we know, other researchers we'll often rely on 1% or 0.001%. So when we retain the null, and the null is true, that's a correct decision. But what that ends up being is it ends up, are we 100% correct? No, we're 1, because everything together is 1 or 100% minus the alpha level. So in this case, 5%. So we're 95%, you know, or not 95% confident, but what's happening is 95% of the possible outcomes will fall within the null, right? Within the body and not the tails or the critical regions. Okay, now let's assume the null is false. And so instead our alternate hypothesis is true. Again, we can make 2 decisions, the correct one or the incorrect one. So if we retain the null, when we're saying there were no differences, when in fact there were, right? The null is false. Then what we've done is we've committed a type 2 error. By definition, a type 2 error is when you reject, or excuse me, when you fail to reject the null, when in fact the null is true. So, or when in fact the null is false. So you incorrectly fail to reject the null. So type 1, I reject the null and error. Type 2, I fail to reject the null and error. So I said that there were no differences when in fact there were, okay? And we represent that by beta. So alpha is represented, type 1 error is represented with alpha, type 2 error is represented with beta. When we reject the null, when in fact the null is false, we've made a correct decision, right? And so again, just like our alpha, 1 minus the alpha is the correct decision. For when the null is false, 1 minus B is the correct decision, okay? So 1 minus the type 2 error risk. And that essentially now translates into power. So power becomes our 1 minus B. So correct decision when we reject the null, because the null is true, that is just 1 minus alpha level. So when the null is true and we don't reject it, okay, meaning we retain the null and it was true, that's a correct decision. It's just 1 minus alpha level. And then when the null is true but we reject it, that's type 1 error, okay? When the null is false, so there were significant differences, but we didn't reject it, we didn't find it, that's type 2 error. And then when the null is false and we reject the null, that's a correct decision, that's your power, okay? So power is your ability to find significant differences when they exist. And so notice our formula is now 1 minus B, okay? And what it ends up doing is it ends up calculating the probability of committing type 2 error. And so we use this as a mechanism before we do a study to look at how much power do we have to find the differences, if in fact they really do exist, to find that treatment effect. And then what we often do then is it's all based on assumptions, okay? So it's all hypotheticals. It's saying, okay, what's the power of the test given X sample size? So given 50 participants, given 100 participants, given 150, assuming we want a treatment effect of D equals 1 or D equals 2, right? And then what we do then is we run those hypotheticals to see how much power we have. Will our power increase if our sample sizes increase? Will our power increase if we assume a smaller effect size? And so it becomes a hypothetical. And I've outlined the steps to calculate a power analysis, but honestly, we use power calculators. And so in your module in Canvas, you will find power calculators that you can link to. And that's what we use, okay? But it starts with choosing your alpha level. We're gonna use 0.05 in most cases. Then you're gonna look at the Z boundaries that correspond to those. You're gonna calculate the standard error for those Z scores, for those Z boundaries. And then you're going to look at what are the X values that correspond to those Z scores, right? And those are going to kind of set your boundaries. And so it becomes this convoluted process, right? And again, I would say just like we use SPSS for the more complicated stuff, use a power analysis, okay? But I want you to conceptually understand what power is more so than doing all of the calculations, okay? So essentially what we're looking at is we're looking at the ability to find significant differences when in fact they do exist, okay? Hopefully that helps. And then let me know if you have any questions.